So now at hand, we have these following building blocks, which mean that, the arithmetic logic unit. Okay, here I have two inputs, A and B, and here's the function, and here's the output. And then I may have some equality, like if they are equal, it will be 0 or 1. I may have a multiplexer, or here's a register file, okay, which has read and write ports, and I also have a clock for a bank of registers. So I know how these work. So what I will do is I will use these blocks in my design of the process. Again, I will skip this. So that brings us to the sequential. So it's sequential hardware. It's a processor, and it works as follows. Let me just show you basically how, this is your first view of how a processor looks like. So everything starts from PC. PC is, program counter. It's a register, and it contains the address of the current instruction. And then we have an instruction memory. And then when we feed, remember this is my address, when we feed this into the instruction memory, then what do you get? You read out the instruction itself, because remember that our instruction is actually stored in the memory, and this is we're pointing at that instruction, and then you'll read the instruction here. And then after that, we call this the fetch stage. Then after that, remember that we have a register file. So we have 15 registers in here. And then to this, then I can feed my source A and source B, which is, I have an instruction. I have read the instruction, like whatever its bytes are. And then as part of the instruction, imagine, for example, I'm adding two numbers from RAX and RBX. Then you have to access the register file and read the values of those two registers, okay? So I should get them. We call this the decode stage. And then comes the execute stage, in which case, for example, once I have these values, then I can pass them to my arithmetic logic unit, add them up here. And for certain instructions, maybe I will be accessing my data memory. Maybe if I want to read something from my memory or write into my memory, then you will get this. And then after that, this is called the memory stage. And sometimes you want to write back into your register file, and this is what we have, this first loop back into the register. And the last thing that we do is the PC stage, which is you compute the address of the next PC and put this as your input to your PC. And all this thing happens during one clock cycle. So this is the duration of one instruction execution. And the sequential processor executes one instruction per clock. So again, to make them clear, we have the fetch stage, in which we read the instruction from the instruction memory. We have the decode stage, where we read the program registers from the register file. We have the execute, where we compute the value or address, like whatever by doing addition, subtraction, XOR, AND, and so on. We have the memory stage, where we read or write data. We have the write back stage, where we write the program registers. And then finally, we update the program count. And when we do this, remember that, since I changed my PC, then what do? Then I fetch the next instruction and then do this over. And then after that, I fetch the next instruction. So this is kind of like an engine that, comes back with the next one. And so it will continue to execute until it's basically ends with the health instruction. Let's look at the instruction decoding. We have already seen how this basically encoding must work. So for example, in our case, we had this possibility, the first 4 bits here, this was always the instruction code, which we call I code. And second 4 bits here, this is the instruction function, we call this I. And then as an optional way, I may have the IDs of 2 registers. This is not true for all the instructions, but for some instructions. So it's optional. So I may have array and RB here. And finally, again, as an optional one, then I may have this displacement, which we call the val_c. This is the value that's represented as a constant word as part of my instruction. So for example, if I want to, if I have an arithmetical logical instruction, okay, like this, this was encoded as such as 6 function, array, and RB. Now, in the fetch stage, I'm supposed to read 2 bytes because this is a 2-byte instruction. In the decode stage, I need to read the operand registers from array and RB. And in the execute one, then I have to perform the operation that's specified by the function, which is again part of the instruction, and also set the condition codes as a side effect. At the memory stage, I don't do anything because this is not something that updates it. In the write back stage, then I update the register, which register RB. And then in the PC update, then you increment the PC by 2 because this was a 2-byte instruction. So to basically make this more formal, I have actually written them in a stage, in different stages. Okay, so here's the fetch stage, decode stage, execute stage, memory stage, write back stage, and PC update stage. And this is how it works. So, like, let's go through. It says that, read 1 byte. Again, now this is like M1 means, okay, read 1 byte, okay, from instruction memory. And split this into 2. First 4 bits is I code, the second 4 bits is IFA. And then, the second byte, M1 at PC plus 1. Remember, PC was the address, right? Address of the instruction. And then you read the second byte, and then this tells me RA and RB. And then at this stage, I also compute PC plus 2. Well, this gives me val P. Val P is the address of the next instruction. I don't need this till the end, till I compute, till the end of this execution. But, given that at the beginning I can compute, it's better to just put it aside, and then you'll use this. And then in the decode stage, then I have like a register array, and let's read this as val A, and the register RB as val B. And what's this? Remember that, in our case we had this register file, right? And in here, what I would do is I would give RA as a 4-bit number, and then I would give RB as, again, another 4-bit number. And then in the register file, you can see that I have all these registers, right? 15 of them. But based on this RA and RB 4-bit values, then I will read from one of them. The value that I will read 64 bits, and I will say that let's call this val A. And I will read another 64 bits here, and I will call this as val B. So this is what we do at the decode stage. In the execute stage, I do val A, op, val B, and op is determined by my IFA, right? And the CC, the condition codes are automatically set. Memory stage, nothing. And in the write back stage, I said RB. Okay, remember in this case, what do I compute here? So this computation that's done is here, like this. Here's my arithmetic logic unit. And I pass this to val A and val B, and I also feed my function ifun here, okay? And the result, I said, let's call this val E. Again, this is a 64-bit number. And then in the write back state, then you again say val E is set into RB, and you can see that I can do this into my register file. I have 64 bits of val E, and then I have 4 bits of RB. And I put this in here. And the last thing is I want to do a PC update. I said val P, which was PC plus 2, and then set it to PC. Okay. So this is basically I'm splitting the computation that needs to be done in discrete stages. What about I have another instruction like rm move q. This is register to memory move. And this has the following things. So RA, and then DRB. Remember, like the task was that, take from register RA, and then you set this, you write this into the memory location by D plus R. Okay, this is what it's supposed to do. So the first thing is that the fetch stage, I have to read 10 bytes because, 1, 2, and then 8 here. So I read 10 bytes. Then in the decode stage, I need to read the operand register for RA and RB. And so I feed them, and you read val A and val B, right? Then you compute the effective address. Well, this is pretty easy. So you have to do the computation of D plus, val B, right? And then we have to write into the memory, okay, which is this. And then in the write back stage, do nothing. It means that I don't have to write anything into the memory. And then in the PC update, we increment it by 10. So how does it work? Here's my stage computation for this. So the first part is easy. The first byte is split into icode and ifun. And then PC plus 1, I read 1 byte, it's RARD, it's the same. And then I have 8-bit bytes here, starting from PC plus 2. And I said, let's call this val C. And then I complete PC plus 10, and so I call this val P. And at the decode stage, it's again the same. Read feed RARD and complete val A and val B. In the execute stage, you feed val B and val C. Now, note this, like this is slightly different from what we have done before. So we have this arithmetic logic unit, right? Different from the first case. In this case, I will be feeding val B and val C. Okay, in the previous instruction, it was val A plus val B. Now it's val B plus val C. And then for the function, I need to put plus or 0. Okay, and the result, let's say that this is called val E. So you compute the val E, and then now we have a memory stage. Now, what's the memory? So we have a data memory, and in a data memory, how do you access the data memory? Like just a regular memory. Well, you have the address, and then you have the data lines, right? What you do is you have, let's say that here's my address line, which is say that it's 64 bits, and here's the data, and that's also 64 bits. What do I do? Once I have this as the address, well, I feed val E, because this is my effective address. And as data, I feed val A, which is also called. And that's it. And no write backstage because my register files are not updated. And PC val P should be updated to PC.